At the turn of the 20th century in Germany, there lived a horse named Clever Hans. The horse's owner, Wilhelm von Osten, claimed Clever Hans could do arithmetic, tapping his hoof a number of times equal to the answer. Psychologist Oskar Pfungst was skeptical but curious. Pfungst decided to test Clever Hans in different situations, sometimes with different people asking questions, and sometimes with Clever Hans wearing blinders. Pfungst discovered that Hans was indeed clever, but not for the reason von Osten claimed. Clever Hans was remarkably accurate, but only when he could see someone who knew the right answer, whether that was von Osten, Pfungst, or someone else. Pfungst reasoned that Clever Hans was reading subtle body language when people expected Hans to stop tapping his hoof, like a slight head nod. Pfungst even learned to read these cues himself in a lab. Only these more controlled scientific tests could reveal what was really behind Clever Hans's impressive performance. In September 2024, OpenAI announced their then-smartest new AI, O1. OpenAI internally codenamed O1 Project Strawberry because it could finally count the number of R's in the word strawberry. Over a year after their AIs could, say, pass the bar exam. AIs are getting much smarter over time, but somehow they still fail tasks that seem simple to humans. These AIs aren't dumb, but their intelligence might not work how we'd naively expect. So to forecast AI's future, we need to act like Oskar Pfungst and test AIs scientifically. In particular, AI researchers can better understand the minds of AIs using techniques and insights from cognitive science that studies the minds of humans and animals. How we study intelligence in people, and why it's hard to apply to AI. People often compare AI intelligence to animals and humans. You might ask if an AI is smarter than a cat, a 2-year-old child, or a PhD student. In humans, we can study intelligence through measures like IQ scores, because many of our different mental skills and capabilities are correlated. A crossword puzzle expert is likely good at multiplying numbers in their head, for example. This effect is called the positive manifold, and it's well supported. It lets us talk about intelligence as one broad human trait, like we do with, say, physical strength. It's hard to say if a champion weightlifter is stronger than a champion wrestler, but we usually say both are stronger than the average person. Similarly, it might be hard to tell if a Nobel Prize-winning physicist is smarter than a chess grandmaster, but we usually say both are smarter than the average person. But even though different cognitive skills correlate statistically, individual people usually specialize in specific areas. You wouldn't hire someone as a physics researcher from their IQ score alone. You'd look at their skills and experience in physics specifically. In AI, this is even more pronounced. Large language models do many tasks, but when people fine-tune LLMs for, say, coding or writing poetry, it concentrates the AI's skills in one narrow area. Going further, a system trained from scratch only to recognize images can do so better than ChatGPT, even though ChatGPT does better at nearly everything else. So even if something like the positive manifold exists for some types of AI, it doesn't tell us as much as it might for humans. So to understand an AI's actual limits, we should zoom in on specific capabilities. But how do we find those capabilities, measure them, and combine them into a fuller picture? Limitations of existing benchmarks. We can start with AI benchmarks, the big sets of questions AIs get tested on. Many modern benchmarks scrape questions from the internet. For instance, the common sense reasoning benchmark Hellaswag, used with LLMs like Claude and GPT-4o, contains mainly articles from WikiHow. Scraping the web gives us a huge number of questions to make large benchmarks, but there's a cost. We can't always verify that the answers are accurate or even make sense. For Hellaswag, around a third of questions contain errors. Even the most common benchmarks like MMLU have lots of errors in important categories. So maybe let's check our benchmarks more carefully. But zooming out a bit, what does a high benchmark score even tell us? Imagine a new AI gets 95% on a mathematical reasoning test. Even if we know what topics were on the test and previous AI scores, we don't know if the AI is actually good at mathematical reasoning. Maybe it saw the answers during training, or there's some hidden pattern in the questions. Think back to Clever Hans. To learn the most from benchmarks, we have to treat them scientifically, deducing what we can from observations about how AIs behave. Lessons from cognitive science. We've dealt with similar problems before. Cognitive scientists build models of the minds of humans and animals, perception, attention, memory, and so forth, and they do this with indirect data they can observe. AIs might have different specific skills, but methods from cognitive science can give AI researchers a head start. To start, let's go beyond a benchmark score and see what types of questions AIs fail at. Check out this score chart on MMLU from the system card for OpenAI's O3 Mini. We see OpenAI's models are improving across languages, but we could be learning more. MMLU has multiple choice questions in 57 categories: abstract algebra, marketing, world religions. How well did each model do in each category in each language? Breakdowns within categories would further help, like perhaps an AI does worse on coding questions about for loops than on other coding questions. We could also see how an AI came up with its answers if it used something like written chains of thought. Evaluators themselves often can't see those. It's also important to clearly report the conditions of the test. To assess a math test for humans, you'd want to know how much time the students had, and if they had a formula sheet or calculators, and so on. Similarly, for AIs, you'd want to know how much compute the model could spend for each question, what information they were prompted with, and if they used tools like a code interpreter. This isn't always made obvious. The numerical scores could also say more. These scores are just proportions. We can see which are higher or lower, but that's about it. If AIs A, B, and C score 0.4, 0.6, and 0.8, you can tell C is better at the test than B, which is better than A, but the jump in skill from A to B isn't necessarily the same as from B to C. On average, guessing randomly on a 4-answer multiple-choice test will give you around 0.25. But maybe the first 40% of questions are easy for AIs, or the last 20% are really hard. And since AI test scores increase so fast, we'd also like to compare an MMLU score with harder tests like GPQA, Humanities Last Exam, or Frontier Math. Ideally, we'd score all AI benchmarks with only one unit of measurement. The best units of measurement work like meters. A 1-meter high box stacked on a 3-meter high box is as high as a 4-meter high box. But less literal units help too. IQ scores work statistically. The average score is 100 points, and the standard deviation is 15 points. So when psychologists observed that IQ scores in many populations worldwide have increased by about 3 points per decade, psychologists can use that specific fact to make hypotheses and predictions, and readjust the scale. A good unit of measurement for AI capabilities, like for IQ scores, wouldn't just show that capabilities are increasing, but how quickly. Researchers already have tools that might help, like observational scaling laws, which let you predict an AI's results on many different benchmarks from a few underlying ability scores. Notably, these laws still hold for so-called agentic benchmarks. These measure how well AIs complete entire tasks, like fixing buggy code or operating customer service chats. Their results are usually also reported as proportions. For example, Anthropic's Claude 4 Opus passed 72.5% of challenges in the bug-fixing benchmark SWE Bench. Learning how an AI approached each task could tell us even more for multi-step agentic benchmarks than question-based ones. Validity. Besides reporting results more effectively, we can also design tests to have more meaningful results. Here's what cognitive scientists look for when designing tests. To start, test the entire capability you're measuring and nothing else. Don't make a general arithmetic test without subtraction problems, or a grammar test where you score higher with neater handwriting. For AI benchmarks, ensure the questions weren't memorized, are on topic, and have no unintended patterns, like how in one multiple-choice benchmark, shorter answers were more commonly correct. Tests that work across different environments and groups of test takers are more useful, like a test for both humans and other great apes. For AI, this might mean tests usable for AI models with various skill levels, specializations, or architectures, or even by AIs and humans and animals. Finally, your test should predict real-world capabilities, like how children who excel on memory tests learn new words more easily. A basic prediction for AI benchmarks might say how well the AI answers real users' questions on the same topic. More complicated predictions could say how the AI improves with more training or other enhancements, or how well its skills extend to other topics. Cognitive scientists consider these parts of a test's validity, in particular, construct validity. how well a test actually measures what it claims to measure. It's hard to meet all these criteria even when testing humans, but the more valid a test, the more specific and confident we can be using its results to make predictions. We also want specific, precise working definitions of the capabilities we're measuring. Ideas like theory of mind or common sense reasoning have their own implications, history, and associations from cognitive science. Defining these terms rigorously has helped develop better ways of assessing them. Using them improperly might convince us an AI has other capabilities, or even moral standing, when it's unwarranted. Or it might conceal these systems' real power. So, when you see an AI's impressive benchmark scores, consider what those results actually mean. Try to eliminate alternative explanations. For example, did the AI memorize the answers? Some AI models can reproduce the exact list of multiple choice options on some MLU questions from memory. Varying details on the questions and the exact phrasing of the multiple choice options, or having a set of questions that's kept out of training data, can give us confidence the AI isn't just memorizing each question's wording. Conversely, if an AI scores poorly on a benchmark, maybe we're asking the questions poorly. For a long time, animal psychologists used the mirror test to see how self-aware animals were. They figured an animal which found a mark on its body using a mirror must be aware its reflection was its own self. Chimps and dolphins found the mark, while dogs and elephants didn't. Did this mean dogs and elephants were less self-aware? Well, dogs have poor eyesight, but a great sense of smell. Dogs can pass a sort of smell mirror test. They recognize their own scent on unfamiliar objects and notice when that scent is subtly altered. Meanwhile, one Asian elephant passed a mirror test with a simpler change, a much larger mirror. This principle could also apply to AIs. The ARC Prize challenges AIs to find patterns in grids of colored squares. Though it's meant to test how well AIs generalize knowledge to novel tasks, today's top AIs are better with text than images, so the difficult part might actually be reasoning with visual information specifically. A similar quirk could explain the strawberry problem. LLMs see words as numerical tokens rather than sequences of letters like humans do, so counting letters is less natural for them. Improving benchmarks is just the beginning. Cognitive scientists often seek explanatory mechanisms. What systems in a subject's brain caused their behavior? Right now, evaluators rarely get more than just inputs and responses for cutting-edge AI models. More information, like chains of thought, probabilities of different outputs, or even a model's actual parameters, could help open the black box of neural networks for clues on how they work. Existing work. Some benchmarks already use the ideas we've presented, including ones designed by cognitive scientists. We'll showcase some using classic problems in cognitive science, but the same best practices apply to any skill. The Baby Intuitions Benchmark, or BIB, compares the intuitions of infants and AIs. AIs have changed a lot since the original 2021 BIB paper, but BIB's methods showcase the power of cognitive science tools. In the paper, AIs watch moving shapes acting as agents on a computer screen. 5-month-old infants expect an agent to reach for an object they've taken several times before, even if that object is in a new place. But the AIs tested with BIB didn't display that expectation. The authors give details about the AI's performance on specific tasks and subtasks, videos of all the trials, and examples of specific video frames where an AI succeeds or fails a trial. For another task, AIs watched agents get keys to unlock a barrier, keeping them trapped, letting them reach a goal object. Once the AI learned the agents would get the key to escape, the experimenters tested the AI on 3 similar scenarios. One had a locked barrier trapping the goal instead of the agent, one had a way around the locked barrier, and one had no barrier. In all 3 cases, the AI predicted the agent would go straight for its goal, ignoring the key. Using their more valid tests with well-reported results, the researchers could deduce that the AI didn't generalize its knowledge to the new layout. BIB's original AI subjects were convolutional neural nets, basically image predictors. Today's LLMs would certainly fare better. Still, BIB is a good example of a rigorous benchmark that helps us make hypotheses and inferences about the AIs we're studying. Another good test is CogBench, a collection of 7 classic human cognitive psychology experiments adapted for large language models. With just these few questions, researchers have found that AIs trained using human feedback behave more like humans do in these experiments. One more example is Animal AI. a simulated environment for an AI to interact with, containing cognitive tests like those used for animals. They test skills like navigation, object permanence, delayed gratification, tool use, and numerosity, the ability to tell how many objects there are somewhere. AIs may be a new kind of intelligence, but we don't have to reinvent the whole field of cognitive science from scratch. And we don't have time to. AIs are getting smarter incredibly quickly. We need to take the task of measuring their capabilities very seriously and have good tests ready well before we expect AIs to actually get good scores on them. And beyond measuring them, understanding the way AIs think is a critical step on the path to AI alignment. The more tools we have available to do this, the better we can prepare for the future. Cognitive science might just help us avoid catastrophe. If you're interested to learn more and try to help, our top recommendation is for viewers to take the AI Safety courses by Blue Dot Impact at AISafetyFundamentals.com. The courses consist of a selection of readings curated by experts in AI safety. They're totally free, and you can just read through them at your own pace. There's also a live version run remotely, where you have weekly calls with a facilitator and others doing the course. Plenty of Blue Dot alumni have gone on to work full-time in AI safety, so it's a great place to start.